There we go. Can you hear me? All right. Any questions before we start? Looks like we're missing Mia and Morgan. Okay, so lab, there was a request to have lab due on Wednesdays because if it was distributed on Monday, you would only have 2 days to really ask questions outside of or inside class before the Wednesday class, and then it was due again, then it would be due Monday. But if we had a Wednesday, a few more days to look at it before asking any final questions, I think that's a great idea. So let's do that. We'll have it due Wednesday. This week's lab 2. So you can turn in lab 1 either today or before Wednesday is fine. Lab 2, we need some more material to finish. So we're going to talk about probability distributions and moment matching in the next week or so. So that will be due, I think, probably 2 weeks from today or 2 weeks from Wednesday. So a little more time on this one. It's a pretty big one, so I would get started early and take a look at it, do what you can, and then maybe some of those concepts, as you see them appear in the lab, we'll cover those in class. Okay. So any questions on that? All right. So today we're talking about deterministic models. Deterministic models are going to be an important part of developing our hierarchical models. When we talk about hierarchical models, there's usually 3 components. There are data models, which describe uncertainty in the parameters that we're discussing. There are process models, and these process models are usually where these deterministic models fit in. They describe some underlying ecological process that we're interested in learning about. So to characterize the process, we have to use mathematical models that describe the process, or roughly describe the process we're interested in. And then on top of that, we usually have data models, which describe uncertainty in the data collection process. Okay, so today, deterministic models and how we use them in hierarchical modeling. When we use these models, mathematical models, we don't assume that these represent truth. The middle quote here is often used when describing statistical models, in that all models are wrong, but some are useful. So I would argue that most scientists don't actually believe the deterministic models that they're using represent the true reality perfectly. Ecological systems are complex, and it would be impossible to capture all those complexities using a model. So we use these as representations of reality that'll help us learn something about the system that we're interested in. So art is the lie that makes us realize the truth. Looking at these models, we're going to use those to say something useful about the system. All models are wrong, but some are useful. And then it is better to invent reality than to try and copy it, because copying it mathematically would be impossible. So here we have the change in population growth, or the logistic growth model that represents how much population changes for each time, how much n changes, dn dt. So Mia submitted this model, I believe, as her process model. Is that right, Mia?
Yes, that's right.
Oh, okay. Yeah, so this is a common deterministic model used in ecology, probably taught in all ecology courses, where we have R represents the intrinsic population growth rate, N is population size at time t, and then K is carrying capacity. Now, I don't think anyone would actually say populations grow logistically, but that this model represents some important concepts that we have, in that as the population gets closer to some threshold, there becomes less resources, and the population change, the change in population decreases. So this is a useful function that gives us some properties that we know actually exist in reality. But whether or not this function is true or represents true reality is not really the point. It's that it's a useful model that describes some useful properties of the system. There are a lot of other models that do this same type of thing. So ultimately what the function of this model does is give us the sinusoidal shape. Let's see. Where we have time on the x-axis, population size, and it gives us a shape that looks something like this. So there are a lot of different deterministic models that'll give us something like this. And they all have some form that look kind of close to this, and the exact form of that deterministic model, we can describe each of these parameters with respect to the system we're studying. So things like Gompertz models, the Robert May model we described in lab 1 looks something like this too. We saw actually how that process changes through time depending on the values of the parameters. So the point is, we want something that looks like this, because this is how we think populations may change roughly. And there are a lot of different deterministic models that will give us this. Okay, so going back to the goal of the course and our line of reasoning for scientific insight. We start out with current concepts, theory, and questions. In that, we develop models that represent conceptual hypotheses about our processes, and then we tie those models with data to observations, and then we gain new insight qualified by uncertainty. So we're going to talk about the models that we often use for ecological systems. And it turns out the upshot of this is there are relatively few models, mathematical equations, that represent a huge field in all of the sciences. All right, so how do we actually link our deterministic models to data? Well, we start out with our idea, and in the case with logistic growth, the idea was we have some population that doesn't increase exponentially through time, and that there should be some limitation based on resources. And then when that limitation starts to be hit, the population starts to not decrease, but increase slower. And there's some asymptote related to carrying capacity. That's our deterministic model. That represents our idea. And then we have to develop a mathematical equation to conceptualize or to quantify that idea. And then we're going to try and tie that model to data and estimate the parameters of that model using the data. And where the statistics comes in is we're going to use this body of theory that describes probability. In the next few lectures, we're talking about deterministic models today. Wednesday, we'll be talking about the basic laws of probability. Monday, probability distributions, and then Wednesday, we'll get into likelihood and Bayes' theorem. So I think the lab covers the first 3 of these topics. So we will probably have the lab do either 2 Wednesdays from now or the following Monday. Stay tuned on that. Okay, so what are we going to be talking about today besides deterministic models? Or what about deterministic models? I mentioned this idea of support a couple times in the previous lectures. So we're going to actually talk about what that means, because we want to match the support of our data. If you've taken an introductory statistics class and you have data that don't necessarily meet the assumptions of linear regression, what is the main tool you use in trying to meet those assumptions?
Could that be a non-parametric test?
Okay, right. So you have in So let me start off asking a simpler question. What's the main tool we use in statistical analysis? I don't know if this is obvious the way I'm asking this. Okay. Um, the first thing you learn about in a statistics course when you're trying to compare X to Y.
I feel like I'm going to be wrong, but linear regression.
No, that's exactly right. Simple linear regression, right? We want to compare X to Y. And when we do linear regression, there's these assumptions of these models that the data are identically distributed, they're independent of each other. The errors are homoscedastic. Now, we check the assumptions of that model, and then after we check the assumptions, we may find that some of those assumptions are not met. Then what's the next step? What do we do? And this is, we have a hammer, and that hammer is linear regression. Let's try and make everything look like a nail. So how do we make things look like a nail in simple linear regression?
You do a data transformation?
Exactly. We transform the heck out of it until it meets the assumptions of simple linear regression. We take the log. If the log doesn't work, we take the square root. Square root doesn't work, we take, I don't know, log base 3.7 until we can get that into a simple linear regression model. And then we meet the assumptions of our data. And if that doesn't work, we use mixed effects models where we put a random effect in there and call things random effects and fixed effects. Okay, so that idea is we have this tool that's pretty useful, simple linear regression based on a normal distribution. Let's see if we can get all of our data that we've ever come across into that framework. So what we're going to talk about in this class is this idea of support and what the support of the data are, and then choose the appropriate tool to match the support of the data. So more about exactly what support is later. Distinguish between purely empirical models and models symbolizing processes. This is something that didn't occur to me until later on in my graduate schooling, when I got a review back from a journal. I was submitting a PhD paper on my PhD research on survival rates of cackling geese. And what I had done was developed a purely empirical model that described what the survival rates were from 1982 to 2010. I said, here are the survival rates, this is what they are. And the reviewer comment was, okay, you've described what the survival rates are during that period, but you haven't really told us why that's useful for the future. It's basically all empirical. You said what they are, but you haven't said what they are. So distinguishing between purely empirical models where we're just looking at correlation between one thing and the other, and then model symbolizing processes where we have some hypothesis about how a system works. We develop a model to describe that process, and then we validate whether that process really was generating data that we collected. So if the model we had a hypothesis about of how the ecological process works, if that model actually can generate the data that we observe, then that lends support to that model being credible, or support for that model. Okay, we're going to introduce a set of functional forms useful for composing deterministic models. In all fields of science, there's essentially a few deterministic models that are used, and then in each different field of science, they get their own name. There are some cross-cutting themes we'll talk about. This is the first one I had just mentioned. A relatively small set of functions can be used to describe a broad array of not only ecological processes, but physical processes, processes used in engineering, medicine, all fields. The same process can be represented by different functional forms. And this is what I was talking about with the idea of growth being limited by resources, where we have some process we know where growth will increase until some point, and then will begin to increase at a decreasing rate. And there are lots of different functions that can represent that exact same process. And then on the other side, the same functional form can be used to represent different processes. There are some good books that talk about this for ecology. Ben Boker is a quantitative ecologist in Canada. And he talks, you also see his name a lot on our forums. So if you're wondering how to do something and someone asks a question, he's usually one of the, and it's related to ecology, he's one of the first people to respond. Then Otto and Day have a book, A Biologist's Guide to Mathematical Modeling in Ecology and Evolution. So the idea behind these books are, how do we use these mathematical models to represent the hypotheses that we have? And it becomes an important part in statistics. All right, so deterministic models. The study of calculus is about the study of functions, and then doing things to those functions, like taking the derivative and integrals of those functions. So if you recall from calculus, a function is where we have y is some outcome that we can describe that as some function of x. So y is on the x-axis, y is on the y-axis, x is on the x-axis. Usually in calculus, we talk about continuous functions. Let's see. Where we have x and y, and we have some continuous function of x, where this line equals some function of x. So we put x into some function, and it gives us an output. We choose any value of x here, we go up to the line, and then it'll give us the value of y. So choose a value of x, go up here, and it tells us what that y is. We're going to use, as I mentioned, the first day of class, we're going to use y for data. So we're not going to use y equals f of x in this class. Instead, we're going to change y to mu. So mu equals f of x, and mu is going to be the value on that line. I'll also oftentimes refer to mu as the expected value of the function of x for any value of x. So what's another word for expected value? This one you may not have heard of. I mean, you have heard of it, but putting the two together. So another word for expected value is the mean. The value you would expect if you were to collect some data on a process. So the mean mu of I is also going to be the mean or the expected value of x. We'll talk a little bit about more of this later. So now f of x can be any one of those functions that you are going to use to represent your ecological process. So I had you send me one deterministic function that's used in your field. And that's essentially what f of x is. It's going to be deterministic, meaning we give it a value of x, and we're going to get an output value for mu. The other addition we're going to add to this basic function is the parameters. So we're going to be interested in estimating parameters in our statistical inference. So we're going to include that in writing this out. Now recall, when we write out parameters, generally, we're using theta. So let's look at an example of this. I'll start with a new line here. We have x, we have y. Let's use our very simple function, the equation of a line. We'll say mu of I equals beta 0 plus beta 1 xi. This is the intercept. This is the slope. We give it the value of x. and then we will get an outcome of mu. And that can look like this, for example. Or it could look like this, or this, depending on what the value of beta 0 and beta 1 are. And we're going to try and choose the best values of beta 0 and beta 1 from our model. Now in calculus, they always tell you what beta 0 and beta 1 are. There's nothing about estimating these parameters. They say, suppose you know beta 0 and beta 1. What's the value of y if x equals this? And then there's more complicated forms of this, right? More complicated functions. But in statistics, what we do is we estimate beta 0 and beta 1 when we have data. So if we have this, we try and estimate beta 0 and beta 1. And that's what our output is from R. When we fit lm y tilde x, it gives us beta 0 and beta 1. We looked at that last week. And in Bayesian inference, it's going to be the same thing, except we're going to have posterior distributions for beta 0 and beta 1. All right, now back to the slides. We said that this is our function here. This is y equals beta 0 plus beta 1x. I'm sorry, mu. Or we could write this as mu I equals some function of x and beta 0 and beta 1. And then for shorthand, we say these are theta. Because sometimes we'll have models that have hundreds of these parameters, beta 0 through beta 100. We don't want to write them all out. Instead, we can just write for shorthand, this equals theta. The parameters equal theta. That's what the shorthand is right here. Okay, so that's some notation on our function. Again, mu I is the expected response, xi are predictor variables, and then theta will be the parameters we're going to estimate. What makes this deterministic? The fact, what makes this deterministic is that if we provide an x, there's only going to be a single output. There's a single spot on that line for any value of x. So deterministic models are all the models that you see in calculus. Now, I kind of wish I could retake calculus and think about all of the different ecological theory I've learned since I first took calculus, and appreciate that as we're learning those functions that they talk about in calculus, the functions they describe in calculus are essentially the few functions that apply to all fields of science that I was talking about earlier. So I wish I could go back, take calculus for a fourth time. That I'm serious about that. And sit in and think, well, that would be a good function to use for this process that I've been thinking about in the past. Having that context behind actually learning these functions instead of just learning functions without really understanding why we're learning these functions. Okay, and then we talk about one of the basic forms of the functions that we use is beta 0 plus beta 1x, where theta equals beta 0 and beta 1. So this is what I went through in that example. Now, what f of x and theta is going to represent any process we're interested in ecology. Some examples are the spread of white nose syndrome. So this is something that a colleague and I worked on where we were trying to figure out what would be a good mathematical function to describe how white nose syndrome, which is a fungus that occurs in bats that affects their hibernation, how that would spread through time. If we could actually come up with some function that describes how it moves from one spot to the next. And we went to mathematics and we found the appropriate functions to use for these were something called partial differential equations that we would have taken in calculus 3. Decomposition of grasslands and soil. So if there's some function that describes how grassland decompose. The movement of elephants across landscapes. So how an individual animal, how would you write out a function to describe how an individual animal moves from one spot to the next? Food web dynamics, growth of waterfowl populations, influence of hydrologic regime on riparian plant communities, invasion of exotic species into native plant communities. So all of these can be described, or you can come up with mathematical models that will describe these processes. Now, again, they're not going to describe them perfectly, but you can find useful models that will help quantify these movements. And once we have those deterministic models, then we can start thinking about putting that deterministic framework into a statistical framework so we can estimate uncertainty in our parameters. So here are a few of the mathematical models that are commonly used, at least in the things that I study. Linear models are common across all fields of science. Probably the most common tool for inference. A t-test is the form of a linear model. Nonlinear models. Things become more complex when you add nonlinearity. The mathematics isn't quite as nice. Things become harder to estimate, but most things in real life are nonlinear. Systems of differential equations, if we're working in continuous time, or systems of difference equations if we're working in discrete time. Integral projection models, it's a type of matrix model where it's broken up into continuous space. This IPM idea are becoming popular buzzwords in ecology. State transition models is a discrete form of an integral projection model. So matrix models, Leslie matrices or Lefkovich matrices are deterministic models. Any equation or system of equations making a prediction that can be compared with an observation. So our task in the end is going to be to interface our observations with these models to estimate parameters. All right, so how do we talk about functions now, this f of x and theta, where x are covariates and theta are the parameters we're going to, that describe what the model looks like exactly, and then that we want to estimate. How do we actually combine that with our data? And the way we're going to do that is with these probability distributions. So we talked about the notation here where we have this notation here with the square bracket represents the probability distribution of y, and then the up and down line is conditional on our parameters. So mu is a parameter that describes the mean, and sigma squared describes the center, the spread of that distribution. So mu is the peak of this, and then sigma squared describes the dispersion. So this could be, for example, this bracket here could represent a normal distribution where mu equals the mean and sigma squared equals the variance. So mu could change, it could go to the left or it could go to the right, and sigma squared could change, it could make this shorter and wider or taller and skinnier. And what this distribution is going to allow us to do is for any value of mu and any value of sigma squared, it's going to describe the probability of observing data for those values. And we're going to choose mu and sigma squared that maximizes that probability, maximizes the likelihood. All right. Normal distribution is most commonly used distribution in all fields of science. Now we're going to talk about this idea of support. And one of the reasons for recognizing that the normal distribution is not always a great distribution is to understand its limitations. The normal distribution goes from negative infinity to infinity. That's what we're going to call the support of the normal distribution. meaning that any value between negative infinity and infinity has some small chance of being observed. Now, despite this being the most commonly used model in all of ecology, it's often a poor choice. Any guess on why that may be?
Does it have to deal with just the fact that the larger systems are, the maybe there's more opportunity for entropy, and so like chaotic distributions and randomness within natural populations?
Yeah, that's a good answer. The data may not be normal, right? You might have extreme values that come out, 100-year floods that are very poorly described by normal distribution because of their rarity. We observe a lot more in ecology than would be predicted based on a normal distribution. Normal distribution, essentially, when you get without three standard deviations of the mean, that's essentially a 100-year event. It's so rare to go 3 standard deviations away from the mean that it only happens one time every 100 years. So 99% of all your observations within a normal distribution should be within 3 standard deviations of the mean. However, what we see is a lot of extreme events in ecology that are not well characterized by the normal distribution. And we have other distributions that do that. Distributions with so-called heavy tails or fat tails, where the tail on this distribution is actually much wider and it doesn't go up quite as tall as a normal. Okay, so that's one good reason for not using a normal distribution, this over dispersion idea. There's other reasons too, and I'll tell you one of them. So if we don't transform our data, I talked about how transforming data is the #1 tool to get everything to look like a normal distribution. But what if we don't transform our data? What if we try and keep our data in the format that it was collected? There's a lot of good reasons for doing this. Interpretation is a good reason why we might want to keep our data in the units it was collected in. Comparability to other studies. Anyway, there are a lot of good reasons for keeping the data in the natural support they were collected. If we do that, how many, can you think of any case where the data that you would collect fall between negative infinity and infinity? So that's the support of the normal distribution. It goes between all the way down to negative infinity, all the way up to infinity. And I'll compare that to a couple other distributions shortly. So are there any data that you can collect in its natural units that actually fit within that framework? And I've thought about this quite a bit, and I can't think of any.
Perry, by that, do you mean just like we will never have like that sort of magnitude of spread in natural data that we collect to like fully like use that full range of normal distribution?
That's part of it, yeah. But the other part is if I go out and try and collect precipitation data, I'm never going to have a negative value of precipitation. It's always going to be positive unless I do something to that data. And the normal distribution always has some non-zero probability of observing negative data. It may be small and inconsequential, depending on what the spread of that distribution is. So for practical reasons, it may not be that big of a deal, although there are a lot of cases where it actually does affect our inference. All right, support. So let's formally talk about support. Support refers to the range of values that a variable can realize. So a formal definition will come soon. So what is, as an exercise, what is the support for the following variables? Soil organic matter content, grams of OM divided by grams of dry matter.
Well, that's not going below 0, right?
Right, yeah, so that's positive or non-negative. Observed survival of an individual. What's the support of that, Morgan?
I think that would be positive too, right? Because would that be like if the animal survived, it was a 1, and if it didn't, it was a 0?
That's exactly right. So positive is not right, but 0 and 1 is right.
Okay.
Positive would be, it could be like 1.2 or 9,226. But 0 and 1 was what you said, and that's right. Yeah, so 0 and 1 are the support of observed survival of an individual. Species richness. I guess it depends on how you define species richness.
It would be a lower bound of 1 for only detecting one species, and then I suppose, I don't know an upper bound, but positive.
Right. Or if you didn't see any species 0, presumably it could be a 0 too. But the non-negative integers, 0, 1, 2, 3, 4, 5. Carbon flux. Flux is a rate of change. So here we might get something that looks more normal, but again, that's because we're doing something to the data. And then above ground biomass of a grassland. Biomass would be positive. Not the integers, but any real value greater than 0. Okay, so all of these different units have different support for the data. And what we're going to want to do is match the support to the statistical theory that are used for those types of support. Any questions about this?
Yeah, Perry, when you mean match support, does that mean like when you're specifying, say, in a linear model, because I feel like most of us are kind of comfortable there, like what the family of that would be for like, the survival, that would be like family equals binomial type.
Yeah, exactly. So you've already done this, right? Without maybe knowing it. So when you're describing a generalized linear model, and you can choose between 0, 1 data or count data, and you have to say the family equals binomial or the family equals Poisson. That's exactly what you're doing. You're matching the support to your data. That's a good example. Okay, so let's talk about some of these functional forms, going back to deterministic models. Now, when we were talking about support, we're going to be talking about how we match the statistical distribution with our deterministic functions. But before we get into that, let's talk about some example functional forms for this f of x theta. Because as I've mentioned a couple of times, there's really only a few different variants of these mathematical functions. And when you start to see them, you start to see all these other functions that have names. And we'll talk about some of these at the end and some of your functions at the end that fit into these broad categories of functions. So we have additive effects, asymptotic processes, and power functions. Additive effects would be like a linear model. How do we compare x to y, or how do we draw a line? Asymptotic processes is similar to logistic growth models, where there's this diminishing returns on our population size as x increases. And then power functions. We see power functions a lot, and they describe how things decay or increase. All right, additive nonlinear models. These are probably the, as Kelly, you mentioned, the simple linear regression models. You're familiar in this zone. This is what these additive nonlinear models are. Additive models contain linear functions of coefficients and predictor variables. So we have the expected value mu equals beta 0 plus beta 1x plus however many terms you want to put in here. Now, when I'm saying additive, there can be some confusion in this because this doesn't necessarily mean a straight line, but it means we're adding the betas plus beta times x to something else. That it's additive in the coefficient or the parameters betas, beta 0, beta 1, all the way up to beta d. So one function you've probably seen is something like this. Use my finger. Okay. This is x, this is y, and our function of x equals beta 0 plus beta 1 x plus beta 2 x squared. Right, this is how we get a bend in our line. So we have a higher order polynomial that gives us this parabola here. And it allows us to have some nonlinear relationships in the data. Allows us to model this bend in the data because we have this polynomial here. This is still in statistics considered a linear model, even though we have this nonlinear looking line. And it's linear because we're adding beta 0, we're adding all these betas. So it's linear in the betas. So this still falls in the world of linear modeling. Okay, so when we talk about additive models, we're talking about additive in the betas. Now, the other place of statistics you might be familiar with are generalized linear models. These are generalized because we are going to be doing something to the beta 0 plus beta 1x plus all the way up to however many covariates we have d, beta d plus x of d. We're going to be doing something to that to change the support from negative infinity to infinity. So this part right here, the support of this is negative infinity to infinity, because if beta 0 and beta 1 and beta d can take on any values between negative infinity, and they can give you a line anywhere that you want. When you think of a line that's not flat, it's going off to infinity and negative infinity on the other end. So the support of this is negative infinity to infinity, but often we want to use this framework, adding these betas, because we're comfortable in this area, to describe the relationships of other types of data we observe, like the probability of success or some positive value. And that's where we get into generalized linear models. We do something to this to make it match the support of our data. For example, if we take the exponent of this, the values are always going to be positive. And that's going to match data that are only observed in the positive world. If we are interested in probability of success, we can transform these values here so they always fall between 0 and 1. Any idea on one of the functions that we use to make that transformation? This would be what you're doing when you say family equals binomial in R. Or the link equals. We often have to describe what the link is.
Logit.
Logit, yeah, or actually the inverse logit function is going to convert that beta 0 plus that everything else to be between 0 and 1. So that's what we're doing. We're taking this framework that we're comfortable in and then matching the support of the data that we're actually interested in. There's other, logit is one function we could use. There are other ones. There's probit function will do similar things. Clog function will do similar things. Logit's the most commonly used one because of it has, well, two reasons. One, because it has nice interpretation in terms of the log odds. And the other one is there's some theory that supports why we would use the logit function. It's called the canonical log function, and that has some nice properties to it. All right, so let me just plot this. To show exactly what we're doing when we do these generalized linear models. This goes off to negative infinity. This goes off to positive infinity. And let's do an example. Let's do the logit function. Or let's say we want to convert our values between 0 and 1. We could use logit function or probit function or clog function. But anyway, here we have on the x-axis beta 0 plus beta 1 x. So these would be our values of our linear model. When we plug in beta 0, beta 1, and x, it's going to give us some value on this axis. And what we want to do is do something to that to convert it between 0 and 1. So we're going to want a function that looks like this. It'll take very negative values of beta 0 plus beta 1x. So let's say beta 0 plus beta 1x equals negative 5,000. And so that would be way over here. And we want that to be close to 0. We want, when these values are very negative, we want it to be close to 0. And then when these values are very positive, we want that to be very close to 1. So we need some function that does that. And the inverse logit function is one that does that. But it's not the only one. There are an infinite number of functions that will convert, that look something like this. That convert values that go from negative infinity to 0 and 1. And we'll use some of those functions. The most popular one, though, is the logit. So we'll use that mainly. When we start talking about more advanced hierarchical Bayesian models, like occupancy models, there are some very nice reasons for not using the logit function, for using the probit function instead. All right. These generalized linear models and linear models are usually empirical models. So they're very useful for modeling the correlation between predictors and responses, but they're less useful for understanding why those correlations occur. So we talked about one of the objectives of this lecture is to distinguish between purely empirical relationships and more mechanistic relationships. So if we're just looking at the relationship between X and Y, we can fit a model and interpret the model and say, well, it looks like these data are correlated. And maybe that tells us something useful. The alternative would be we develop a mechanistic model that we think supports reality, and then we compare that model to what the data is that we observed. So we have this a priori hypothesis development. We examine that model, compare it to data, and see if it does a reasonable job of predicting the outcome. And then we can say something about the process of that model that we're using and why. Okay, so we talked about this a little bit already. What if the response variable is between 0 and 1? So not just 0 and 1, like survival data or observation data, but what if we actually observe any value between 0 and 1? Here are some examples: proportion of plots with invasive species, nitrogen content of soil, proportion of a landscape burn, survival probability of juveniles, or prevalence of disease in a population. So we haven't talked about a type of model that would be used to match the support yet. This one is less common in ecology, but still used quite a bit. Let's see. In terms of, does anybody know off the top of their head what type of model we might use for values between 0 and 1? This one is used a lot less. The one that comes to my mind is something called beta regression. Have you heard of that term? Beta regression. Beta is a distribution. The beta distribution is a distribution that the support is any value between 0 and 1. So if you have response values that fall between 0 and 1, then we can use beta regression to model those without transforming to the normal scale. All right. Now, let's talk a little bit about the inverse logit function, because in my experience, many people use this function whenever they do binomial regression, but there's a lot of uncertainty in what's actually going on and how to interpret these functions. All right, before I go into this, do we want to, we've been going for 52 minutes. I say we take a couple-minute break. If you have any questions, we can address those now. So let's just take a breather for a minute here. Hi, Angela.
Hey, Perry.
Good to see you.
Yeah, thank you. I was very happy I could make it this morning. Thanks for letting me sit in. I missed last week, but I was able to catch up on your posted lectures on
Oh,
YouTube.
good.
That's
good.
a cool thing. I didn't even know that you could do that with YouTube. Like it could integrate within Web Campus. So that's a nice feature.
Yeah, I used that last semester, and that's
Yeah.
I think the one thing about shutting everything down is putting material online. Students seem to appreciate that and have that recording available.
I was on sabbatical last semester, so I wasn't teaching, and so this semester is like my big introduction to teaching over Zoom.
Oh, okay.
Oh, wow, you can do that, and you can do this.
Did you?
And I
were you
like
able?
the recorded lectures, and I think for graduate students, it's amazing. I'm nervous about undergrads because I'm afraid they're not going to show up if I record a lecture.
Yeah,
We'll see.
and what I found too last semester was when the graduate class has been great so far. I look at the panel and I can see everybody, and people seem to be interacting. But when I was teaching undergraduates, it was always everybody had their screen off. And then even after you say, all right, everybody, can we turn our camera back on? They turn it on, and then gradually they start to fade away, and pretty soon. And I have no idea if anybody's listening or if anybody's even there.
Yeah, that's it. I mean, if my screen's on, I'm not there, basically. It's like, I'm not listening. Because, at Colloquium, we have all of our screen, like, we turn our screens off. And it takes me 5 minutes to lose interest if I don't have my screen on and I'm not, like, actively participating or listening.
Yeah. When we first started using Zoom, I'd always turn my screen off because I thought, oh, it would just be distracting to see me. They don't want to see me. They just want to do this. But then after teaching, I appreciate when people have their screens on.
Absolutely. I do too. I want to see faces.
Yeah.
I don't want to see your name. And I want to see people's cats,
All right, show of hands, who's heard of the inverse logit function? Let me see, okay. Looks like most people have heard of it. And all right, let's talk about inverse logit function. So we have Kelly made a great point earlier that said, you know, we're familiar with this idea of beta 0 plus beta 1x. We're all pretty comfortable in this world. Let's say mu I, our expected value equals beta 0 plus beta 1 xi, where we know beta 0 represents the intercept, beta 1 represents the slope. And we know how to interpret that. So the interpretation of beta 1 would be for each unit increase in x, the expected value mu of I increases by beta 1. So that's our interpretation. And that makes sense to us, right? Now, we want to, so we're going to want to hold on to that idea. We know what to do with this. But when mu of I changes, or when our data is not necessarily between negative infinity and infinity, we're going to have to do some other stuff to still hold on to this beta 0 plus beta 1x, but also match what our data look like. So let me go back to how we wrote out simple linear regression model, where we have, I'll do it the first way I wrote out, yi equals beta 0 plus beta 1 xi plus epsilon I, and epsilon I comes from a normal distribution with mean zero invariance sigma squared. Now, in this case, yi are any value between negative infinity and infinity. But now suppose we're going to the wildlife world, where we have, whether we observe a species, if we observe a species, it gets a 1. If we don't observe a species, it gets a 0. And there's no good way of linking up this equation with zeros and ones. It just doesn't work. So we have to extend our toolbox a little bit to try and match the support of our data. And one way we can think about doing that is to do a transformation to this so that it's between 0 and 1, and then that will represent the probability of success. And then when we have zeros and ones, we can start thinking about the probability of success as being similar to a coin flip, where if we're flipping a coin, we're going to either get a 0 for tails and a 1 for heads, and that there's some underlying probability, some latent probability associated with that process. And the coin flip is 50%. So we got to do something to this, right? Oops. We got to do something to this to get it between 0 and 1. And one of those functions is, first, let me rewrite this equation a different way so it'll be easier to compare to Bernoulli regression. So let's say yi comes from a normal distribution with mean mu I and variance sigma squared, and mu I equals beta 0 plus beta 1 xi. All right, so last time I talked about how these are equivalent ways of writing out the exact same function. We're going to use this just because it translates over to our Bernoulli regression a little easier. All right, so let's do something to get this between 0 and 1. One of those functions we can do is, let's say that beta 0 plus beta 1 xi equals the logit of mu I. Logit is just a word that represents something else. And what logit stands for is the log of the odds. That's one of the nice reasons logit is used a lot, because it has this interpretation of odds. Any function where you have some parameter p divided by 1 minus that parameter p is called the odds. So this is what, again, going back to gambling, what gamblers use in terms of making wages. You describe the odds of winning versus losing, something like 3-to-1 or 2-to-1. So whenever you see this quantity, mu I divided by 1 minus mu I, or p divided by 1 minus p, or psi divided by 1 minus psi, any of those are called the odds. And so we have the odds here, and we're going to take the log of those odds, and that's what the logit represents. Logit is just shorthand abbreviation for this longer function here, so we don't have to write this out. So let me give a couple of examples on the whiteboard. Logit of p equals the log of p over 1 minus p. If we use parameter psi, it just equals the log of psi over 1 minus psi. So you get the idea, right? We just have to, if we wanted to write this out, we take the log and do the odds. So the odds p equals. And then if we take the log of both sides here, okay.
Perry, sorry if this is a dumb question, but log is not, it's referring to the natural log, right? Not log base 10.
Yeah. So in all of mathematics and statistics, log is always the natural log. It's only in engineering when you start using log base 10. So we'll always talk about natural log here. All right. So now let's, and what this does is when we do this function to p or to phi, it converts it to values between 0 and 1. And that's what we want. So this is one function of x, or function of phi, that'll convert it between 0 and 1. And there are actually lots of functions that will do this, but the logit function has some nice properties. So that's why it's commonly used. So this is going to convert, take that back. This value can be anywhere between negative infinity and infinity, and that's why it's nice. All right, it's after we do the transformation that, let me get back to that. So let's say the log odds of mu I equals beta 0 plus beta 1 xi. We know this can be anywhere between negative infinity and infinity. So this can be anywhere between negative infinity and infinity. But we're going to eventually want to get mu I by itself. Because when we do our Bernoulli regression model, we're going to say our data yi come from a Bernoulli distribution, not a normal now. We're switching to match the support of our data. Bernoulli is a binomial distribution with one trial. So it's like flipping a coin once and describing if you get a heads or a tails, where a heads equals 1, tails equals 0. And then mu I is going to describe the probability of success. So this together is the model statement for logistic regression. This is how we would write it out statistically, what logistic regression is. And to fit this in R, we would say GLM y tilde x family equals binomial. And it'll give us estimates of beta 0 and beta 1. It won't give us estimates of probability of success. We have to know how to get those ourselves. All right, so we need to get mu I by itself. So in algebra, to get something by itself, we have to do things to both sides of the equation and try and rearrange things. So until we get it by ourselves. So that's essentially what we do with mu I. We need mu I by itself. We know it's between, has to be between 0 and 1. We want to do some stuff to it, stuff to this to get it between 0 and 1. All right. So let's do some stuff. Let's do the algebra here. We have the logit of mu I equals beta 0 plus beta 1 xi. And then again, yi are our data, our zeros and ones. These come from a Bernoulli distribution with probability of success mu I. So how do we get mu I by itself? Well, let's write this out. How do we undo a log in algebra? If we have the log of 2,
Exponents?
exactly, yeah. Exponent is the inverse function of a log function. So we take the exponent, I'm looking ahead at the algebra and I want to, this is all true. We could do it this way. That'll just be a little trickier. So I'm going to do something else. One of the log rules that you may not be familiar with unless you've dusted off the rules of logarithms recently is if you take the log of mu I divided by 1 minus mu I, this is also equal to log of mu I minus the log of 1 minus mu I. Okay. So the log of A divided by B equals log of A minus log of B. This is one of the reasons working in logs is nice because it changed all these divisions and multiplications into addition and subtraction. So if, let's see. Yeah, the opposite of that is if you have log of A times B, that equals the log of A plus log of B. So these are just rules. So we can use these rules to try and get, the goal here is try to get mu by itself and see what that looks like. And after we go through the algebra, it turns out that mu I equals the exponent of beta 0 plus beta 1 xi divided by 1 plus the exponent of beta 0 plus beta 1 xi. So we do the algebra to this side of the equation and this side of the equation. Oh, I'm sorry, this side and this side. And this is what we get. And there's a couple other ways of writing this. I think I have it down here. Yeah, so we can also write it. There we go. You can also write it this way, depending on which steps you do, which algebraic steps you can do. either one are equivalent. This equals this. So now we have mu I by itself. We have still this component in here, our linear regression model. But we have to do this function to beta 0 plus beta 1 x to get this to be between 0 and 1. So mu I is now going to be between 0 and 1 after we calculate this.
Perry, we're still on your slide.
All right. Thank you. So now going back to calculus, here's our f of x. F of x and our parameters beta in here, we'll just call those theta, equals the exponent of beta 0 plus beta 1 xi divided by 1 plus the exponent of beta 0 plus beta 1 xi. And that looks like, if this is beta 0 plus beta 1 xi, and this is that function of x I just wrote, it looks like either like this if beta 1 is positive, or like this if beta 1 is negative. And it describes how this probability of success, we'll call it mu, the probability of success changes with changing values of x. So if x increases and we have this positive function, then the probability of success is going to increase. But if beta 1 is negative, it flips this thing. And then as x increases, the probability of success is decreasing. Now, why the probability of success should follow the exact shape of this function? I would say there's not necessarily a good reason that it has to follow these shapes. This is just the assumption that we're using this logit function. And the logit function gives us this shape, this relationship between x and y. So this line here is mu, or we could say f of x and theta. There's a lot of different names for things at this point, right? We have the function of x and theta. We also call it mu, and this equals the exponent of beta 0 plus beta 1 xi divided by 1 plus the exponent. Okay, so this is the exact functional form. This is f of x and theta. Different values of beta 0 and beta 1 are going to give you slightly different relationships of this line. You could go in R and plot this for different values of beta 0 and beta 1 and see how this shape changes with x and y. And this is what we're using as our function for describing the relationship between x and the probability of success. Any questions about this?
Hey, Perry.
Yeah.
Are those are the y-axis values 0 and 1, but the x-axis is still negative infinity to infinity, right?
Exactly. Yep. Yep. Now, any other questions before I pose a question? Okay, if I were to plot the data on this graph, what would that look like? So remember, data are y's, and there's zeros and ones in our logistic regression setting. What would that look like?
When, depending on whether beta is greater than 1 or less than 1, wouldn't that just be like a clustering at both of the upper ends of the y and lower ends of the y?
Yeah, right. Let me follow up on that a little bit. What do you mean by upper ends and lower ends of y?
Yeah, like if beta is greater than 1, so positive, I would expect like some dots like around 0, like at your leftmost y or your leftmost x-axis, and then some clusterings around 1 at your rightmost. x-axis.
Yeah, that's right. So let's think about this in an Excel spreadsheet. We have a column for our data y and a column for our data x. We don't know what beta 0 and beta 1 are until we fit the model. But when we collect data, we have zeros and ones for our y's, and then we have some covariate of interest x. So our y's are going to look like zeros and ones. And our x's can be whatever they are, depending on what we think is related to x and y. So let's put this in terms of an example. Let's say y is whether or not we went out and marked some sage grouse in Nevada. We put collars on them, and then we released them. And then we went back the next year and we tried to find them. And if we found them, they got a 1. And if they didn't, they got a 0. We didn't find them, they got a 0. And presumably, if we didn't find them, they died. And if we found them, they survived. And now let's say x is some value of vegetation, forb vegetation that it helps survival. Could be anything. This is just an example. And let's say x equals -10, 20, 0, -3, 25, 15, right? This is all we have. This is our data. And from this, we come up with all this other stuff. We say, well, we have 0 and 1 data. That seems like we should use something like a logistic regression model or a Bernoulli regression model because we're interested in comparing vegetation, this index of vegetation quality to survival. So if we actually plot the data on here, like Kelly was saying, we have, if beta 1 is positive, which we think it would be in this case, we're going to plot just these pairs. So 0, let's say this goes from -10 to 25. Here's 0. I'll plot the points in red. We have -10 for x. It was a 0. So here's the plot of the data. It's this one. This one we have 1 and a 20. So if you plot the data, it's here. And then this one we have a 0 and a 0. So 0. The y-axis I haven't described yet, but this is 1 and this is 0. So this bottom line is 0. This top line here is 1. So we have 0 and 0, which gives me 0 and 0. There's a point right here. 0 and -3. Y is 0. X is -3. And eventually, when you plot all the points, you'll have points on the y-axis. They're always on 0 or 1. And then x-axis can be any value between -infinity and infinity. And what we're doing is trying to fit a line, this sinusoidal line, to these kind of group data. And the line is determined by what beta 0 and beta 1 is, and our assumption that it is this inverse logit function. All right. This function, another name, just a couple more notes on inverse logit function. The name, or on this function, this function, the exponent of mu I, no, let's not do that. The exponent of beta 0 plus beta 1 x I divided by 1 plus the exponent of beta 0 plus beta 1 xi. This is called the inverse logit function because it's the inverse of the logit function. It's the function that undoes the logit. So if we have the logit of mu I, there we go, share my board here. If we have the logit of mu I equals beta 0 plus beta 1 xi, and we want to get mu by itself, we do the inverse of this. So logit inverse of the logit of mu I equals the logit inverse of beta 0 plus beta 1 xi. Because we're doing both sides of the same equation to both sides, the right-hand side and the left-hand side, we can do that in algebra. So when we do the inverse logit of the logit, these cancel out. We have mu I, and that equals this inverse logit function, which is this. All right, any questions about that? Going back and forth between inverse logit and logit is an important skill to have, because when you're working in R and you say GLM y tilde x family equals binomial, it's going to give you these beta values here. But it's not going to tell you how this function converts to mu I. So how to get that actual probability of success from those values. You have to know that relationship. There are some specific packages for analyses that will do it, but I think the general GLM function won't do it for you. But if you're doing some more specified analyses and you download a package, some people have written into those functions how to actually go from beta 0 to mu I. Here's a question. Why would they give us in R? You know, beta 0 and beta 1 are useful for describing the how our response variable changes with respect to our predictor variable. But oftentimes what we're really interested in is the probability of success, mu I. So why would they give us beta 0s and beta 1s in our output and not mu I, or the probability of success? I think there's a couple or a few good reasons for it.
Well, for one, using the log odds can be useful for describing actually like the relationship of the betas to your response.
Yeah, so if you're talking in terms of betas, you're describing change in the log odds, how log odds change with respect to your covariates. So you have the interpretation component. So beta by itself is useful for describing that. Yeah, so that's a good point. So beta, what James is saying is beta is still going to help us describe how the log odds of success change with respect to X, which can be useful if we know how to think in terms of log odds. Although log, I don't really know how to think in terms of log odds. Like, I'm not sure what a unit change in log odds means. Odds is a little easier to understand. And the probability of success to me is the easiest way to understand. All right, anything else on why, any other reason why they might give us betas instead of convert it to the probability of success for us? I have two reasons that might be useful. One is it's a deterministic function, right? So if we know the relationship and we know what beta 0 and beta 1 are, we can always get mu. We can do that ourselves. It's always going to be the same. The other thing, the other reason comes to estimating uncertainty in the beta zeros and beta ones. So when we plug in y tilde x family equals binomial in GLM and we say summary of that model, it's going to give us an estimate of beta 0 and beta 1, and it's also going to give us an estimate of uncertainty associated with each one of those parameters. Now, those uncertainty calculations are only good on the scale of the betas. They don't translate well over to the scale of the mu's. So while it's easy to calculate uncertainty in beta 0 and beta 1, it's much more difficult. So for example, if we want to calculate 95% confidence intervals on beta 0 and beta 1, that's easy to do. But it's much more difficult to calculate 95% confidence interval around the probability of success. This is a nonlinear function here. And converting confidence intervals around nonlinear functions is not straightforward. You have to do something called the Taylor series approximation to do that. And this common problem where we want to convert uncertainty in our parameter estimates for beta 0 and beta 1 to uncertainty in our parameter estimates for the probability of success, there's a specific Taylor series approximation that's used to do that, and it's called the delta method. Now, this is only the case in classical statistics or frequentist statistics. In Bayesian statistics, it's really simple. And that's one of the nice things about Bayesian inference, this idea of derived parameters, which we'll talk about. Where if we know our MC-MC chains from beta 0 and beta 1, we can automatically get confidence intervals for probability of success without using the delta method, which we would have to use in a classical sense. So the two methods that I was talking about then are, well, James mentioned one, in that the betas themselves are useful interpreting how the log odds of success change with each unit change in X. The other ones were, it's a deterministic function. So if you know this relationship, you can automatically get mu I. And then the third one is, it's much easier to estimate uncertainty around beta 0 and beta 1 than it is around mu.
Perry, so commonly when people use this sort of like logit function in a model for a paper, do they just sort of describe the results as empirical and correlational and don't really talk about like that kind of how you used in your first publication? That's what you mean by like not talking about how it's actually interpreted as a success. It's more just like this growth rate is positive based off the way you modeled this data.
Yeah, so if you have a function, I mean, if you have a function that looks like this, you're saying essentially as X increases, Y increases, or as X increases, Y decreases. The expected value of Y decreases. That's pretty, there's not a lot of, I'll say it's context dependent, right? There are some simple relationships that you think there might be just a mechanism that it's a straight line. But in most, I'd say 90% of cases, when you're doing this straight line relationship, you're just looking for the correlation in X and Y. Now, I say that with some hesitation because if you design an experiment to look at a specific mechanism and you have a lot of theory that's already built into how your design was developed, then a simple difference in beta 1 here for difference in X could describe mechanistic relationships. So let me expand on that a bit, because that won't make a lot of sense without some background. Let's say I have the ability to conduct an experiment. Experiments give us the best inference, the strongest inference that we can get scientifically, where we change one variable, one control, one treatment, and look at that. So let's say that we have an experiment we're interested in. We think that doing something to the system is going to either change it for the better, change it for the worse, whatever the example is. And we have good reason for why we think that is. So if we can develop a mechanistic hypothesis of why we do something to a system and it'll go up or down, then that's the exception to what I'm talking about. So, okay, we have some plots. We can develop an experiment. We are so lucky to be able to do this. And here we have our control. And here we have our treatment. Now we developed some theory that says if we do something to our treatment, whatever it is we do to them, they're going to be different than our control because of some mechanism. So we're going to apply this treatment and then see what happens. In this case, with a controlled experiment, the model for a controlled experiment is this. Beta 0 then is the effect of the control, and beta 0 plus beta 1 is the effect of the treatment. And if beta 1 is large, it means there's a large difference, either positive or negative, right? So this is identically equal to a t-test. And the output will give you the exact same thing if you do a t-test in R. So now here, back to your question, you have a simple relationship just described by the equation of a line. Let me plot this for a graphical representation of what's going on. So we have x equals 0, x equals 1 here. We have our 4 units from our control, the y values, and then our 4 units for our treatment. We're still fitting a line through this. Beta 1 represents the slope of this line. The mean here is going to be beta 0, and the mean here is beta 0 plus beta 1. So back to your statement, we have the simple linear regression, but I'd say this is far from empirical because of the way we designed the study. So if you design it with this idea in this control and treatment, and you have a hypothesis for why the control is different than the treatment, it's some mechanism of what's going on with when you put the treatment in, why it gets bigger or lower, then I would say this is not necessarily empirical. But that's because we put all this effort into the design. Now, in most cases where this applies is we don't have a designed experiment. We go out, collect data on X, and we go out and collect data on Y. And then we fit a linear regression model. And then we say, okay, as X increases, Y tends to increase. I would say that's an empirical approach. And that's probably 90% of what goes on in ecology when we can't do true experiments, right? So there's a lot to say about how you design your experiment and in these interpretations. In my field, wildlife ecology, it's essentially impossible to do an experiment with wildlife because we don't, first of all, we don't know how many there are or where they are, so we could never randomize on them. And second of all, just the logistics of actually capturing animals for controls and treatments would be extremely difficult. But that's not to say we can't learn about them when we can't do experiments. It's just the inference isn't as strong. All right, let's get back to this. This is what we looked at this inverse logit function where beta 1 is positive. It looks like this. It's the y-axis between 0 and 1. Yeah, when beta 1 is negative, it decreases. So we have the sinusoidal function. And there are a lot of functions, again, that look like this. You don't have to use inverse logit. All right. So why do we bother with this? This goes back to why not just transform the data so we can use simple linear regression. We know that maybe a response variable is between 0 and 1, but maybe simple linear regression would be okay given our data. So here's a case where when you have a hammer, simple linear regression, everything looks like a nail. We have daily survival rates between 0 and 1, but we still use this simple linear regression model. We're just going to add our covariates. We have x and x squared. So this is beta 0 here. Our intercept beta 1 would be 0.001 times x, and then beta 2 is negative 7 times 10 to the negative fifth times x squared. That gives us this function here. And with that, we can get some p-values, f statistics, r squared fit. Why wouldn't we want to do this? Well, what happens when we estimate 95% confidence intervals and it goes above 1? What does that mean? What does it mean to have uncertainty greater than 1? What happens if, for whatever reason, this function goes above 1? There's no restrictions on this function. How do we have over 100% survival rates? So there's some issues with using simple linear regression when we have different types of data. And those often affect interpretation. The other issue is the assumptions of this model assume that these data can be anywhere between negative infinity and infinity. So we're violating the assumption of the model. Pragmatically, would this be okay? It was published. There may be some issues. All right, so now what if let's move on from data that falls between 0 and 1. What if our response data is between 0 and a? Well, we've seen this function here already, e to this linear equation, beta 0 plus beta 1x, divided by 1 plus e to that. All we have to do is multiply by a here, and that gives us a function that gives us this sinusoidal function that goes between 0 and whatever a is. So it's a simple transformation to convert data not just between 0 and 1, but between 0 and whatever we want that maximum bound to be, whatever a is. All right, what if a response must be greater than or equal to 0? What transformation can we use here? This would be GLM y tilde x family equals Poisson, for example. Write this out. We want to use our same linear function. But now we want to convert these to positive numbers. What would we do to them? What's a good function to convert things to positive?
You square it.
Square it. Square it will turn it positive, yeah. That's true. That's one of them. Square both sides, or I hadn't thought about that. That'll always give us a positive value. Ah, okay, I know what the issue with that is. So you have beta 0 plus beta 1. X looks like this, let's say. Now, when we square it, what happens to our lambda? And this is lambda. When we square this function, it's going to make negative values become positive, and positive values become positive. But the values that are more negative are going to be way more positive. So we'll get something that looks like this, right? So now what we're saying that when we square this function, something that's really negative is going to be equivalent to something that's really positive. So maybe there's some cases where that is what we want. But in general, what we want to do, one of the rules, this is something that I haven't talked about yet. What we want to do is maintain a property of our transformation. So if we have a line that goes from negative to positive and we do a transformation to it, what we want to do is make sure that if this value is less than this value here, so let's call this A and this B, we want A is less than B. When we do, after we do that transformation, that function of our line, we want to make sure that A stays less than B, maintain that ordinality of those numbers. When we square that, that doesn't necessarily happen. So that's one reason squared is not used as often in these transformations. I'll go ahead and say what the most common one is we take the exponent of it. Because this is going to maintain that property where if A is less than B when we take the exponent, it's going to look like this, but A is still going to be less than B. It maintains that ordering. Okay, so that's the answer, or at least the most common answer, is we take the exponent of it. So if we go back, we would write the exponent here. That's our function of x. And that's going to give us a line that looks like this. And this is often written as this, log of lambda equals beta 0 plus beta 1 xi. And that's just because if we want to get beta 0 plus beta 1 by itself, we take the log of both sides. So the log of the exponent and the log of this side gives us this. And that fits very naturally into Poisson regression. So GLM y tilde x family equals Poisson. And this is what I talked about in those slides here. All right, here's the upshot, right, of these mathematical functions. There are a ton of different theories, postulates, formulas in all different fields that take these functions and give names to them, depending on what your field is. Let's see, Meredith on. Yeah, Meredith. Meredith, do you see your function in this table that you sent me?
Yeah, it kind of looks like the one in the top right, or the one below it, I guess. Either one of those.
All right, let's look at the next slide. Okay, so Meredith sent me Lambert-Beer law, depth of light penetration. this was the function that she sent me. This is something you use in your field. Do you want to describe this a little bit, Meredith?
Yeah, so IZ is the irradiance at depth Z, and I0 is the radiance at the surface of a water level. So then as you go through the lake, KD is your extinction coefficient for the light, and then Z is your depth. So it just determines how much light there is at a certain depth.
Yeah, very elegant function, has some nice theory behind it that fits into the specific field of science. There's interpretations of each one of these parameters. Let's go back a slide. We have I0 times e to the negative something times something. Let's look at the negative exponential function here. We have a times e to the negative something times something. So the Lambert-Beer law is just a specific case of the negative exponential function. So this is what I'm getting at with all of these theories and all these different fields. We have these basic set of mathematical equations, and we take these equations because they're useful. These deterministic functions are useful for describing how something behaves in all of our fields. So we can take these basic set of functions, apply them to all these different fields, and then give interpretations to each of these parameters. So we can give interpretations to A and negative B and X, like Meredith just did with the Beer-Lambert law. So this is why I said I wish I could go back through calculus, take it again, look at all the functions we learned, and see how those would apply to my specific field that I'm interested in, what new functions I could use. I guarantee there's a bunch of functions they talked about that would be useful that I completely forgot about. All right, Mie-Cent discrete logistic growth equation. It's the sinusoidal function. This isn't, we talked about this with kind of the inverse logit function. And this has similar form to inverse logit function, but we have some rate that gets multiplied by the growth each time. Anyway, so this fits into these class, not one of these specific functions, but the sinusoidal function we talked about with like the inverse logit function. Here's some from last year, some more functions. Morgan, I think you sent me a function too. I didn't have time to input it before class. But this is, Chris Wolf took this last year. He was in the anthropology department. He's looking at human structural growth. He's got this additive function here, beta 0 plus beta 1x plus beta 2. We can call this x2 or some transformation of x1. So a linear regression model. The Ricker model. This looks a lot like negative exponential growth, like Meredith's model, Beer-Lambert law, where we have something times e to the negative something times something. And the function looks just like this. So Ricker model, which is really a prevalent model in ecology, is identical to the form of this Beer-Lambert law, which is used in stream ecology, the same functional form. Steve Ramada talked about Arrhenius equation, where again, we have this negative exponential model. The point here with all these different functions are, they're all built on essentially the same building blocks, the same type of functions. And these functions are ubiquitous across fields, and they all have different names for them and all have different interpretations of the parameters. But if we understand some basic functions, we can use these to understand how we can quantify ecological processes. Holing type 2 functional response, Holing type 3 functional response. Okay. So that concludes our model on deterministic functions. The upshot is there are a few different mathematical functions that parameterized in certain ways can cover a broad array of academic disciplines and subdisciplines within disciplines. And understanding how those work and interpreting those parameters becomes important. Any questions? Okay, so with that, I will see you on Wednesday. We had initially the lab was due today, but there's a request to have it submitted Wednesday so that if you had time if you wanted to ask questions about it on Monday, you can. So I'd be happy to answer any questions about the lab you have too. And we'll just say those are due on Wednesday, sometime at 4 or 5 o'clock. The next lab won't be due for a couple of weeks because we have to cover the material yet. Probably 2 weeks from today or Wednesday. Okay, thanks everyone.
Hey Perry, real quick.
Yeah.
I've been having some issues with some formatting things in LaTeX. Could we go over some of that?
Yeah, sure. Let me let you share your screen.
Sounds good.
It's not compiling?
No, it's not that. It has more to do with, well, for one, like the cache won't work.
Oh, I see. Okay, the R&W stuff.
Yeah.
Okay. Yeah, understanding that cache is you have to understand it to know how to use it. So
Right,
maybe
yeah.
okay. All right, so you can share your screen if you want to share that.
Sorry, I got a lot open. So basically so first things first was like I can't get like the code to like pop up in the boxes like you have on your documents.
Oh,
Mine
okay. So
won't-
what you need to do is go to RStudio.
Okay.
You're working in Sweave instead of Knitter, which was the precursor to Knitter.
Oh, okay. I got you. Hold on.
So if you go to Preferences in RStudio, there's going to be a Knitter/Sweave.
Okay. It'll open. All right. Cool. So tools.
Go to maybe it's editor code. I'm not sure exactly. Maybe just go to RStudio and then Preferences.
You guys can see my screen, right?
Yep.
Okay.
Scroll. Go to the left to RStudio, and go down to Preferences.
Right.
Now you have that Sweave menu on the left.
Mm-hmm.
Change that at the top to Knitter. There you go.
Okay.
Apply that. And then you can close that and then recompile. Project option unchanged. Yes. It may require you to
Do it again because I think that changed global and now it wants it to do this.
Okay, sure. Yeah, hit OK, and then I think you'll have to install the Knitter package, but go ahead, try compiling that.
Okay. The only issue is this for loop takes like 10 minutes.
Can you change what it's looping over? Just make it like 1 or 2 things and then change it back after class?
Yeah. That might mess with the code is the only issue.
Oh, okay.
Because I have it all.
Okay. Well, try that. I think that'll work.
Okay, try that. And then unfortunately I have to run to class. So
Okay.
the only other thing is maybe I can email about you, but like the plots, when I put it into the PDF file, it'll only show like this one, and then it only shows 1 dot for the rest. And I'm not quite sure if maybe that's like a size issue. But I can email you about that if you want.
Yeah, let's talk. We'll have some time after class on Wednesday.
Okay.
Well, then it's due. Yeah, send me an email.
Okay.
We'll have to meet. We'll have to find a time to meet.
Sounds good.
Discuss this. So send me an email when you can meet.
Yeah. Okay. We'll do. Thank you.
Okay. Yep.